By the end of this video, you'll be able to build a neural network yourself and completely understand what is going on over here. Do not forget to subscribe and hit that bell button. And without any further ado, let's get started! So this is a 2D image of what you just saw. This is called a multi-layer perceptron. It is far too complex for us now. Instead, let us simplify us to this image. As surprising as it may sound, we can get back the original network using this simple network. We can simplify this further by having a single node for input, a single node for doing our ML magic, and a single output. The first node is called the input node because that is where the input goes. The last node is called the output node. You guessed it, because it is where we obtain the output from. And all the nodes between these will be called hidden nodes. Now let us make a simple classifier. Imagine if I want to classify whether a dot is black or white. This may sound irrelevant, but it will make more sense as we move forward. We take our black dot and try giving it to the input node. But this will not work because a computer only understands numbers. We can convert the color to its pixel value. All the pixels on your screen range from 0 to 255, 0 being the minimum intensity or being turned off, and 255 being the highest intensity. So we give 255 as the input. Now what happens inside the hidden node? Let's expand the hidden node to see what happens. We can divide the node into two parts. One part is where we multiply it by a weight and add the bias, and the other part is where we pass this output through an activation function. If you are new to this, it may sound like a lot. So let's go slowly. The weight is the parameter of the node. This is the value that an ML model tries to adjust during training. For a quick refresher, consider watching my video explaining ML. Then we can take this value and pass it to an activation function. These are non-linear functions, i.e., simply put, they allow the network to learn complex patterns and relationships in the data that a simple straight line like a linear function could never capture. It will make more sense with an example. We take our black dot, convert it to 255, then we multiply it by a weight. For simplicity's sake, let us take the value as 1, to which we add a bias. For now, we can keep this 0. Quick aside, why do we need to add a bias? Long answer short, if we do not do that, all the planes we construct that will pass through the origin. If you are still curious, I have attached a longer answer in the description. Getting back. Now we have the output as 255 and we need to pass it to the activation function. Now what should be our choice of activation function? To figure that out, let's see what we want our output to be. We know we want to classify it as either black or white, so it is a binary choice. We can assign simple numbers for these classes, like 1 for black and 0 for white. Now, how do we construct a classifier that will give us 1 if the value is closer to black and 0 if we are closer to white? Well, we can set a simple rule like if the value is greater than 127, return 1, otherwise 0. This kind of all or nothing step function isn't used in practice because it's not differentiable, which is a mathematical property our magical backpropagation algorithm needs to work, about which we will talk in the next video. So when we give 255 as the input, the hidden layer converts that to 1. Now this one goes to the output layer. The output layer also has a linear function and an activation function inside it. And that's it. The most basic idea of a neural network. That was in fact the perceptron, the most basic neural network. Now let's expand it a bit, and when we do not know the right values of weights and parameters of the node. So now we have two nodes in the input layer. Multiple nodes together are called a layer, keep that in mind, with 3 nodes in the hidden layer and a single output. Now we will check if the input we give is a 1 or not. We give an input, now what? Let's look at each node. Each node gets the value of the input, and the lines from the input to the node can represent the weights. So we can write for the first node of the hidden layer W11 for x1 and W12 for x2. These get multiplied, then a bias is added. Finally, this is passed to an activation function. Similarly for the second node and so on. In practice, matrix multiplication is done instead of individually multiplying these weights and inputs. Now the big question is, how do we find the weights for these nodes? In practice, we first initialize them randomly the way we did in our first example, then train them using backpropagation, the magical algorithm, about which we will talk in the next video. For now, assume it is a magical algorithm that helps us find the most optimal values of these weights which minimize the loss. And now, with this trained neural network, we can classify anything. You may think this a big overstep from our initial image, but not really. If we take our original image and take an input like 8, what is really happening is that this 8 gets broken down into its individual pixels, which is then flattened into a 1D vector, which is then converted into values. These values are then passed to our neural network. The activation function used here is a ReLU function. Then in the end, we use a softmax function for each possible value and take the one with the highest value. Here in this example, it's a simple binary classifier which basically says if the given input is a number or not. What I just described might sound complex, but it is quite simple. Let us understand how that happens by building it out. It is often in practice that the code is easier than everything you learn about the mathematics. So first we start with the architecture. If it is your first time looking at PyTorch code, it may be overwhelming, but it gets easier with time. We first inherit from nn.module, then start writing the architecture. As it is a 28 into 28 image, that is the size for an MNIST image, we need to flatten it first into a single vector. Then these 784 pixel values are sent to our first hidden layer, which has 1024 nodes, and so on till the third hidden layer. Then the output is sent to the output layer, which maps the 1024 values to 10 values, as we have 10 classes, 0 to 9. Now let us look at the forward pass, i.e. what happens when we send an image. First, the image is flattened into a vector, then it passes through our hidden layer one by one, and each output is sent to the activation function, as we saw earlier. Then log softmax is calculated on dimension 1, i.e. each value of the 1D vector which has 10 classes. This gives us the probability of each value occurring. This is a log probability. That is all there is for the architecture. As I said, usually the code is the easiest part. Now moving on to training the model. We define a train function, we initialize our model in train mode, then take batches of the data, load it into our device. For me, that would be a GPU. Zero out the gradients, get the output of the current data using the model, get the loss, get the backward gradients, update the weights, and if it's the 100 batch, print the loss, and repeat. This is how the training function of most supervised models that you will ever encounter looks. Let's see how we will test the trained model. We define a test function and load our model in eval mode. Here, with is a context manager. Basically, it tells that do not store the gradients of the computation. It will make more sense when we talk about backpropagation. We again load the input in our device, get the output, check the loss against the criteria we are using, like negative log likelihood, get the prediction of the input. You may think, should the prediction not come first and should we not compare against that? Not really, because we want to compare the log probabilities against all the possible classes. And that is it for the test code. We can write a simple main function that trains our model in a loop. To generate a video like the way we started, you would need to store the activations of each individual node as well, which you can do using this code. I have added the link of all the code in the description box below. And that's it. You completely understand how neural network works. You should be proud of yourself. Thank you for watching, keep learning, and see you in the next video.